Okay, so let's go back to this idea of runtime and let's think theoretically. So we're going to look at something called the big O notation. So for runtime, what are our useful goals? What we really want to do is be able to distinguish things that have clear, significant differences. So we've already seen two functions with clear, significant differences. If you remember the graph of the 1000 n log n function versus the n squared function, the n squared function required many, many, many more operations to compute its work as n got bigger and bigger. So we want to be able to distinguish between those. So basically we want to know if there's a difference in the order of growth. So really that's what the O and big O notation is about, the order of growth. There are also things that are kind of close cases that may merit looking at more precise details. So we also want to kind of lump all of those close things together into one category or one set. A second goal is to try and ignore the small transient things. So we also saw how in our 1000 n log n function versus the n squared function that there was a period of time when n is relatively small where the n squared variant requires fewer operations, less work. So what are some useful goals? So we'll ignore the transient issues. So again, we'll kind of ignore the stuff that happens when our n, the size of our problem, is relatively small. We'll kind of focus our attention on the idea of the growth of the two functions, so kind of this area between the two curves here. And in particular, what we're really interested in is trying to come up with some sort of an upper bound, trying to find some function that is above another function at all points in time. So we're really looking for some sort of asymptotic behavior. So just to review, asymptotic is commonly used when working with geometry or calculus. So it's about approaching a given value as an expression containing a variable tends to infinity. Okay, so the definition of big O, again, O kind of stands for order, like order of magnitude. We'll have two functions that we want to somehow compare, f and g. They'll be non-negative functions. So for our purposes, the thing that they're identifying is the time or memory being used. So those are typically not negative values. If we're trying to measure the time that an algorithm takes, we won't have a negative time, and we certainly also can't have negative memory. So we'll say that a function f is in the big O of g of n if there exists constants such that c is greater than 0 and n0 is greater than 0, such that for all n's greater than n0, oh gosh, this is kind of confusing. So let's look at this graphically. But kind of the important things to note here are that we're trying to establish some relationship between two different functions. And we've got two different constants that we're worried about that help us kind of establish parameters for this relationship between the two functions. And one of those parameters, the n0, kind of defines a particular starting point. So we'll come back to that when we look at it graphically. By the way, for clarification, the big O notation is about defining a set of functions that are bounded above by something. So a lot of times I'll read our expression here as the function f is in big O of g. Okay, so again, let's try and break this down to the component parts and look at it graphically. So f and g are non-negative functions. So let's look at an example of some functions. So here's this horizontal axis and a vertical axis. It shows two functions, f and g. So if we think about this as all being above 0, as n is greater than 0, so we're kind of always in this quadrant of our plane. Okay, so this kind of seems to be a good fit for the functions we're looking at, where n is usually about the amount of data that we're working with. So it's usually a count, almost always 0 or greater. So let's look at the other components of this. We'll say that f is in the big O of g of n for values c greater than 0 and n0 greater than 0, such that for all our values of n greater than n0, what that's really doing is it's establishing this dividing line, kind of the start point. So what we're saying is, we really don't care about these transient effects that happen early on. What we're really worried about is the region out here. So kind of from what we're saying is after that point, that n0 point, the area between these two curves always has one curve, the f of n, on the bottom, and the other one, the g of n, on the top. We've also included this multiplier here, the c. We'll come back to that in a little bit. Okay, so does this idea of big O meet our goals for runtime and being able to distinguish between our two different cases? So can we distinguish between this 1000 n log n function versus an n squared function? It turns out that we can. So we can see if things are equal, if they're in a particular set. But we can also we can kind of test this two ways. We can see if one thing's in the set of another and if that second thing's in the set of the first thing. And that allows us to get a little bit of contrast and identify whether things are considered essentially the same or different. What about our close cases? Will they all kind of be lumped together in the same set? So the C constants allow us to kind of lump together things that are very similar, things that if we get a newer computer, it may make up for the difference in performance. So that's where that multiplier comes into play. Does it allow us to ignore the small transient cases? Well, that's what that n0 parameter was for, the whole thing about ignoring the small cases, having this starting point and only worrying about the distinction between the two functions after that starting point. Okay, so let's develop a theorem that could help us understand these things a little bit better. So we're going to say that if we've got two functions and f is in the big O of g, we're going to say that if we multiply g of n by some constant a, that f is also in the big O of that new function that's been multiplied by a. Okay, so to demonstrate this, we're going to use our definition of the big O notation. So the big O notation already includes some constant c that can be multiplied by our function for all values of greater than our starting point. Okay, so our f, by the definition of the big O notation, is always less than or equal to c times our g of n. Okay, now for an arbitrary constant a, all we really have to do is kind of substitute in, change our value of c to compensate for a. So anytime we're past our start point, we know that f of n will be less than g of n, and we'll kind of replace our original notion of c with c over a. So the product of these two will cancel the a's out, and we're back to essentially our original definition of the big O notation. Okay, so our conclusion is that basically we've demonstrated that for any additional multiplier a, that it will not change this relationship. If f is in the big O of g of n, when we have an additional multiplier in there, it's still in the additional this new and improved function. So, okay, the big takeaway from this is that we never need to write all of those constant values. We can just discard them. So if we've got a multiplier by something, when we're simplifying our big O notation, we'll discard that multiplier. Oh, by the way, a lot of our proofs here end with the Latin phrase, which means that which has been demonstrated, QED. Okay, so does this big O notation match our intuition about how we think things behave? Let's look at a couple of simple example functions, so n and n squared. So you probably already feel that n squared grows faster, but let's examine this in the context of the big O notation. So can we say that n is in the big O of n squared? So we can go back to our definition and try and identify values of c and n sub 0 and try and prove that our inequalities that are required hold true. So for this case, I'm going to go ahead and just kind of arbitrarily pick n0 to be 1. And remember that kind of gets filled in, and we're interested in every place where n is greater than n0. And for the c value, we'll also pick 1. And remember, that's kind of our multiplier. So what we're trying to show is 1 times n squared is greater than or equal to n anytime we're past 1. Okay. So this is reasonably straightforward. So we can just multiply both sides of our original inequality, n greater than 1, greater than or equal to 1, by n. So our original inequality, multiply both sides by n, and we end up with what we're trying to demonstrate, that n squared is greater than or equal to n. So in this case, we can actually start with our start condition and use a little bit of algebra and demonstrate that our conclusion is in fact true. So let's look at this from a higher point of view. Let's come up with kind of a general strategy for proving these things. So one of our first steps is to try and pick the multiplier constant and the starting point constant that will make the remaining steps of this problem easier. So these both have to be values greater than 0. And then we'll write down the desired inequality, and we'll fill in our value of c. So we're trying to demonstrate something about the function f being less than or equal to c times g. And then this just leaves it to us to try and prove that the inequality holds whenever our value of n is greater than or equal to our start point, n0. So those are the 3 general steps. We'll be using those time and time again as we're working with big O notation. So as an example, does this function, 3n squared plus 11n, would that be considered to be in the O of n squared? Okay, so any intuition about this? Any sort of a guess? So let's go ahead and go through the proof. So again, we'll go through those 3 general steps. We'll try and pick a value of c and a starting point n0. So this is kind of an arbitrary choice. There are lots of things that would work. So let's pick a c of 33 and an n0 of 1. Then our second step is expressing our inequality. So we'll write down the desired inequality, the function being less than or equal to c times the other function. So here's our inequality. 3n squared plus 11n is less than or equal to 33 times n squared. So again, we've filled in our value of c. Okay, and then the third step is prove that it holds whenever n is greater than n0. And remember, our value of n0 is 1. So we're trying to prove that this inequality will always be true whenever n is greater than 1. Okay, so let's go ahead and continue with that proof. Our third step here, trying to prove that the inequality holds. So we're going to apply a little bit of algebra. So what we'll do is we'll transform this so it's an inequality comparing some expression to 0. And that's a really common strategy here. So in this case, I'm going to subtract the left-hand side from both sides. Okay, so subtract it off of both sides, and then we'll simplify the algebra. Of course, on the left-hand side, things just cancel out. And on the right-hand side, we'll simplify the algebra a little bit, and we'll simplify it a little bit more. And now we've got an expression that says 0 is less than or equal to 30n squared plus 11n. Okay, and remember that these inequalities, you can also read right to left instead of left to right. So I could read this as 30n squared plus 11n is greater than or equal to 0. So again, when you read it right to left, be sure that you read the inequality backwards appropriately. Okay, so using that approach, what we're trying to show is that once we get past our starting point, once we get past 1, that our expression 30n squared plus 11n is greater than 0. And we can accept that this is true based on our understanding of algebra. A square of a positive number will always be positive, and positive times a positive will always be positive. So we've got 2 positive numbers being added together. Okay, so let's take a step back and try and generalize that proof so it'll apply more broadly. So we'll try and establish a theorem that any polynomial of a particular form can be simplified in the big O notation. So our particular form of polynomial is going to be a summation, and the terms of the polynomial will be a constant on each term times our polynomial variable to some power. And the exponents will start at 0 and go up to and include k. So this is just kind of a generic form of polynomial. So as an example, we might have a0 times n to the 0 plus a1 times n to the 1 plus a2 times n to the 2, and so on and so forth. So just a very, very general form of polynomial. Okay, so basically what this is summarizing is that when we've got simple polynomials with positive exponents, we're going to focus on just the largest exponent. Okay. So in order to prove this, what we're going to do is we're going to pick a value of c. So again, this is going back to our definition of the big O notation. That will be k plus 1 times the largest, or the most positive a. So basically what we're trying to do is we're trying to pick our little multiplier here. So it has some relationship to our multiplier in our polynomial and also our highest exponent. Okay? And we're also going to pick our starting point to be the value of n0 equals 1. Okay, so bear with me here on the next step. So what we're trying to prove is that an inequality holds, that our g is always going to be greater than or equal to our f. And we're going to use the same trick that we used in the last slide. We're going to take our definition of the big O notation, c times our g function, and we're going to subtract off our f function. And our goal is to demonstrate that this combined thing is always greater than or equal to 0. Okay? And remember that we've already picked how we're going to come up with our c. Our c is somehow including in its constant k plus 1 times our most positive aj. Okay, so if we combine together this inequality with our summation, we end up with our summation here is going to sum up from 0 to k, so that's summing up k plus 1 times c over k plus 1 times n sub k. So basically what we've done is we've taken this first term and we've divided it up k plus 1 times and then pushed it inside the summation. Okay? And we're subtracting off each individual term of this. So again, we've just taken this and divided it up k plus 1 times and put it inside the summation. Over the course of the entire summation, it will add back to its original value, and then we're subtracting off each individual component of our polynomial. Okay, so when we've combined together terms, our first term, because of our choice of c, is always going to be larger or equal to the greatest a sub j. Okay? And so this term, just by the way we've chosen our c value, is always going to be greater than this term. So for any value greater than 0 and an n greater than 1, the result of this will always be greater than or equal to 0. Okay, long story short, what does this really show? Okay, at the end of the day, what it's really saying is that we don't have to write the lower order terms inside of the big O notation, that it's actually unnecessary. Okay, so let's take a look at another example. Is 1000 n log n, is that in big O of n squared? So again, just to kind of refresh your memory, we'd actually looked back at this graphically, and we looked at these big orders of growth and what the n squared function looks like in comparison to the 1000 n log n function. Okay, so first off, if we want to go through a rigorous proof of this, we have to pick our values of c and n0, and then we have to try and prove our inequality. So let's pick c to be 1,000 and our starting point n0 to be 1. Again, these are kind of arbitrary choices, although 1,000 was already used elsewhere in the problem, so that may be kind of convenient for our next step. So our goal is to show that 1,000 n log n is less than or equal to 1,000 n squared. So again, the 1,000 on the right-hand side comes from our choice of c. And that was an intentional choice to try and kind of match up with the left-hand side, so hopefully things will cancel out. And we've also picked our value of our starting point, our 1, so we're only going to be evaluating things greater than or equal to 1. Okay, so just like before, we're going to juggle around our inequality by subtracting the left-hand side from the right-hand side, from both sides rather. So we'll subtract 1,000 n log n from both sides. We'll end up with 0 on the left, and we'll end up with our right-hand side, our g function, with our multiplier in there, minus our 1,000 n log n. So we've got 1,000 n squared minus n log n. We'll juggle the terms around and express this as a greater than or equal to 0 relationship. So again, just kind of working backwards through that. Okay, so whenever n is 1,000, we'll look at our start point here, 1,000 n squared, so 1,000 times 1 squared, which is 1, minus 1,000 times 1 times the log of 1 is greater than 0. Okay, so we could say it's proven, or can we? So we could argue that the difference grows as n increases, and we actually saw that in the graph. The gap between these seems to increase, but we only saw it for the limited part of the graph that was graphed. So we'd like to know rigorously that it's true for every point after n0. Okay, so let's see if we can somehow prove that this growth continues. So in order to do that, we're going to consider the derivative of the difference. So the derivative will kind of tell us the direction that the function is heading at an instantaneous point. So the derivative of 1,000 n squared minus n log n is 2,000 n minus 1,000 minus 1,000 log n. And we can make a pretty compelling case that that's greater than 0 for n equals 1. We can just show by example. Okay, but again, can we show that this is true for every place as we continue right on our number line? So in order to do that, we also need to look at the second derivative. To know that it's increasing, we need a positive second derivative. So let's look at the second derivative. So the second derivative of 1,000 n squared minus 1,000 n log n is 2,000 minus 1,000 over n. So just by examination, we can make a pretty compelling case that this is always going to be positive. The thing that we're subtracting off will always be less than 2,000, and as n increases, it just gets smaller and smaller and smaller. Okay, so kind of a quick summary here of what we just experienced. You can use calculus to show that one function remains greater than another past a certain point, even if the functions aren't algebraic. So what we just showed is that both the first and the second derivatives were positive past our start point. So that basically meant that the difference between our two functions was increasing every place past our start point. So oftentimes that's going to be the crucial step in proving that one function is in the big O of another function. So the really important takeaway for this is that big O makes our intuition about one function being an upper bound for another function to be precise. We can ignore the constants and kind of consider things that we want to consider similar to be similar, and we get contrast between the things that will have radically different performance with the type of analysis that we're doing now. So big O matches our current goals, and it was going to be a useful tool for us to compare algorithms.